Hey guys, it's Brian again with part 3 of the manual mapping tutorial on the Guide Attacking YouTube channel. And before we start writing our shellcode, I want to take a quick look at the PE format, because now we're going to dive right into it. So this is how a PE header is built, and it starts with the MZ signature we already checked at the beginning of the code of the manual mapping function. So it begins with the DOS header, then there's a pointer to the NT header, the ELF new member. We already used the machine member to check whether the file is a 32-bit DLL or a 64-bit DLL. We used the number of sections member when we copied the sections in the target process. We used the size of optional header when we got the pointer to the section header. We used the image base member when we checked the preferred image base. And so this is a whole NT header. This is a file header, and so this is the file header actually. This is part of the NT header only, and this whole part is the optional header. And as you can see, after the optional header comes the first section table. So there are several section headers. This is just the first one. And as you can see, we have to add the size of the optional header to the address of the file header, to the address of the base address of the module, to get to the section header. We are going to use a few of the tables here, like the import table, or like the base relocation table, or the import address table. And where is the TLS directory? I can't find it. Here the TLS table. So I just took this image of Wikipedia, as you can see, and hopefully it gives you an idea of how the PE header looks in memory. Good. So let's close this and go back to our code. So after mapping the sections is done, we can actually delete the source data. We won't need it anymore. Source data. And now we are going to make a new function. We declare it at the top. A void function and an call, which is important. Let's call it shellcode. And it takes a pointer to manual mapping data. So the first thing we're going to do is this function. And in the function, it's giving error here. Right? So if pdata is empty, let's just return. Go to my notes really quick. Yeah, shellcode. And we can also check if we could also verify if the members of the pdata structure are fine, like mod, LoadLibrary, etc. But whatever. Let's just assume that worked properly. Now we are going to declare a few. Why is it giving? Oh, come on. I don't have a problem. Second? Oh, I forgot the. Yeah. I don't know why, but it forgot to put STD call here. So now it should work perfect. Let's declare a few variables we are going to use in this function. First variable will be pbase, and we'll use pdata for two things. On the one hand, it will be the pointer to our base address of the module, and on the other hand, it will contain the data we need for the relocation, etc. So reinterpret cast byte pointer data. Probably a static cast will. to reinterpret. Oh, never mind this. Then we'll create a pointer to the optional header, p option. I'll just call it opt. We won't need the nt header, so let's just do some nasty casting. Reinterpret cast image nt headers pointer on the base plus cast image DOS header, just like we did in the manual mapping function before. We're going to get the not that one, the LFNU number to get to the optional header. And I completely forgot to. Now it's correct. Yeah, perfect. We got the pointer to the optional header. Let's quickly grab our function prototypes. Library A, speed data, library auto, get proc address, data, proc address. So, thing is, why am I doing it like this? The problem is we are going to inject this code, and that means we aren't able to call any functions basically. So we have to pass all the functions we are going to need in this shellcode to the pdata structure. And from this structure we can then grab the pointer to. Otherwise we would have to relocate our shellcode, which would be a pain in the ass. So I just prefer to pass the addresses to the functions using this manual mapping data structure. Yeah, let's also get the pointer to the DLL main. And that's equal to separate cast what I call? Yeah, FDLL entry point base plus p optional header opt and address of entry point. So address of entry point is the relative address from the base address to the entry point of the DLL. After that's done, we can start with the relocation process. So first we have to calculate if there even is a relocation data. Well, maybe we were lucky and the image was allocated at image base, and if that's the case we don't have to relocate it. So let's get the location delta by subtracting the preferred image base from the current base address. So p optional header image base. If location delta, and again, if this is 0, there's no need to relocate the image. So if the location delta is not 0, we should check whether there is data to relocate the image. Some images are not relocatable for some reason. I don't know why, but you can choose in the compiler whether the image can be relocated or not. For that, we have to check the image directory entry base relog. And if the size of this directory is 0, we can't relocate the image because there's no data. Why is it showing an error here? Do this? Am I crazy? Whatever. Yeah. So let's grab the first image base relocation entry. Relog data. And reinterpret cast image base relocation p base plus p optional directory data directory image directory entry base relog. Oops, typo. This, okay, this dot virtual address. So what this does is the virtual address member is again the relative offset from the base address to the directory. So this is the first entry of many relocation entries. So while the relog data points to a virtual address, we have to do relocation. So the relocation process is kind of complicated, so let's take a quick look at the definition of this structure. As you can see, it only contains 2 D words, and this word type offset member is commented out. That's because this is an array of undefined size. We don't know the actual size of this array. So the amount of words in this array is the amount of relocations we have to perform in the current entry. And we now have to reduce the size based on the size of block member. Basically, we have to do some simple math. So the size of this current directory is equal to size of block, is equal to the size of 2 D words and the array of type offsets. And so 2 D words plus the size of the array. So the size, the amount of entries would be the size of block member minus the size of the 2 D words divided by 2, or divided by the size of the word. A word is 2 bytes. I know that sounds kind of complicated, but it'll make sense if you take a look at the struct for some time. So amount of entries is equal to block data size of block minus size of image base relocation, which is basically just size of D word of 2 D words, and we have to divide the whole thing by size of word, or 2. You could replace size of image base relocation with an 8 and size of word with the 2 basically, but yeah, this way it looks a little bit fancier in my opinion. Let's grab a pointer to the current relative information, to the array I just pointed out, and that'll be at, we have to read it actually, p relative info. Reinterpret cast word pointer, since it's an array of words, the relog data, and so let me quickly go back to the structure again. So to get a pointer to this member, we just have to add 8 to the current address, so 8 bytes to p relog data, or since this structure is just 8 bytes in size, and the word offset, the word array comes directly after the D words, we can just add 1 image base relocation to it. But also cast this into a byte pointer and then add 8 to it, or we can just read this pointer by 1. Looks easier, and it's basically the same thing. So we got the amount of entries, and we got the pointer to the relative information. So let's actually relocate the image. For u and I, 0, I not equal amount of entries. Plus I and plus relative info. Relative, my bad. So we just loop through all the entries in the array. Now let me quickly explain what this member actually contains. Go back to here. This word consists of 2 bytes, of course, and the high 12 bits are the actual relocation, are the offset to the actual relocation, and the low 4 bits are a flag to indicate which type of relocation. There are several different types of relocation. We only care about one. So let's check. let's actually make a macro for this. It's a lot easier that way. Let's just define it here. So define relog flag 32. Of course, there are two different relocation flags, one for 32-bit and one for 64-bit. Pass the relative info. And let's grab the high for bytes, not the low for bytes. If so, relative info shifted by 12 bytes or hexadecimal OXC. If that's equal to image rel based high-low, based, as you can see here, there are many, only care about this one, then it's a 32 image relocation, and the relative info is image rel based high 64 based directory, sorry, this flag. Then it's a 64 location info. Because I'm lazy, I'm just going to define a macro depending on platform we are currently on. So if def 64, define relog flag 64. And else define relog flag 32. And enter. Perfect. Now we can just use the relog flag macro to check whether the relocation is necessary or not. So if the current relative info, still reference it, is contains a relocation flag we care about, we have to actually Are you giving me an error? Oh, no space here, sorry. Perfect. So if relog flag, get a UN pointer to point where we have at the delta, location delta. Reinterpret location into a UN pointer base plus the current relocation block. And now we also have to add the low 12 bits of the relocation info. So let's grab the low 12 bits. And I'll just put this in brackets as well. So this is a pointer to where we have to relocate it. And now we can just add the delta to it. Get it as UN pointer again. Future Brian here, and in this line I made a major mistake, which is very crucial to the whole manual mapping process. I forgot a plus sign in front of the equal sign in line 148, as you can see on the screen right now. Definitely add the plus sign in front of the equal sign, otherwise the shit won't work. And that's basically it. That's the whole relocation process. After we're done with the current entry, with the current relocation block, we have to go to the next block. So let's just add, not add, but update the relocation data member block, whatever. Cast image base relocation entry. Now we have to cast it into the byte, sadly. Pointer data block plus prelog data size of block, like this. And that's the whole relocation process. that's all real for this tutorial. In the next tutorial, we'll then actually fix the imports and run the TLS and call the DLL main. So that should be the last part of the series.